Hi everyone, this is Mo Hasanovic from Indian River State College. Welcome back to our fiber optic video series. Today we are covering lecture number 6, and we are going to be talking about fiber optic splices and couplers. Just to refresh our memory, last time we introduced fiber optic connectors, and at the beginning of the last lecture we talked about 3 different types of connections that exist in fiber optic links. We talked about fiber optic connectors, and then the other 2 types of connections would be fiber optic splices and fiber optic couplers. That is basically the topic of today's lecture. So today we are going to be talking about 2 distinct types of fiber optic splices, and those would be mechanical splices and fusion splices. Of course, we are going to define what a fiber optic splice means and how it's being performed and what type of connection is established. We also are going to be talking about basic splicing techniques for each type of fiber optic splices, and finally, in the last portion of the lecture, our attention is going to shift towards fiber optic passive couplers that also enable connections between multiple ports. So once more, as a review from the last lecture, fiber optic connections are used to connect various parts of a fiber optic link with a goal of minimizing the loss of optical signal as it propagates through these connections. Each fiber optic link has a transmitting side and a receiving side, and those fiber optic links may be covering very long distances, so very often the total length of a fiber optic cable may not be sufficient to cover the entire distance from the transmitting side to the receiving side. And in such a case, you would have to use multiple fiber optic cables that need to be connected in some way. So one way to connect them, that's been explained last time, was using fiber optic connectors. And today we are talking about yet the other 2 types of connections, and those would be fiber optic splices and fiber optic couplers. Okay, so what do we mean by a fiber optic splice? We are talking about a permanent connection between the 2 optical fibers. In other words, 2 ends of 2 optical fibers with exposed glass core and cladding are being merged into each other and connected in a certain way. In a sense, that's a different type of connection from a fiber optic connectors, where we had 2 connectors mating into each other at the mating surface. Also a fundamental difference is that in the case of a splice, we are talking about permanent joint, permanent connection, while in the case of the connectors, you can disconnect and again reconnect, so the connection is not permanent, as in the case of fiber optic splice. And finally, fiber optic couplers would be connections where we may have multiple ports or multiple inputs on one side and multiple outputs or multiple ports on the other side. Here on the left side, you see an example of a fiber optic coupler where we had one port on one side and then two ports on the other side. In other words, the signal would be split from one single optical fiber into two optical fibers, or in the case of a combiner, the two ports on the right side would act as inputs. So we'll have 2 optical signals coming through each of these ports and then being combined through the coupler into one single output. How is the fiber optic splicing performed? So we are talking about permanent fiber joint whose purpose is to establish an optical connection between the 2 individual optical fibers. The way how this is performed, number one, you have to have a very precise technique that would establish a precise alignment of the 2 mated fibers. So the 2 glass cores would have to be perfectly aligned before the permanent connection is established. This is required so that nearly all the light that's coupled from the glass core from one optical fiber is completely transferred into the other fiber through the junction that's been established through the action of optical splicing. There are two distinct techniques how fiber optic splicing can be performed, and those would be mechanical splicing and fusion splicing. We are going to be covering both of them. On the left side here, you can see an example of mechanical splicing where two optical fibers are brought in a close contact, and then certain transparent adhesive was put in the junction between the two. This transparent adhesive has a very similar optical properties to the glass cores. So in a sense, when the light comes to this junction during the propagation, it will not be refracted or reflected, but it's gonna pass through the junction into the other side, to the other optical fiber. On the other side, fusion splicing is different technique where you're not using some sort of adhesive to make a permanent connection, but you are bringing two optical fibers in a close contact, and then you are applying high current or arc that's going to melt the glass and ultimately establish the connection between the two loose ends of the two fibers that were brought in a close contact. Let's also talk a little bit about the advantages of splices over the connectors. In general, optical splices provide lower return loss relative to the connectors, lower attenuation. Optical splices are also physically stronger than the connectors, and they are less expensive. They require less labor than installing connector onto the optical fiber. The joint is also significantly smaller relative to the size of the connectors, and therefore very convenient to be used as an inclusion into splice closures. The splices also offer better hermetic seal, and it's also important to mention that the splicing can be performed of individual fibers or on groups of fibers, which would significantly reduce the time that's required to establish the connection, as opposed to the connectors where each connector has to be installed individually onto individual optical fibers. This slide briefly describes the way mechanical splicing is performed, and briefly it also describes the actual mechanical splice. So mechanical splices are used to create permanent joints between the two fibers. Two fibers are held in some sort of alignment fixture, such as the one shown on this slide, and then brought to a closed contact. And then the connection between the two glass cores is established through the use of some sort of transparent index matching gel or optical adhesive that matches the properties of the optical properties of the glass, and that's gonna result in reduced loss and reflectance that is gonna be present while light propagates across the junction between the two glass cores. Mechanical splices generally have higher loss and greater reflectance than fusion splices that we're going to be talking about in the slides that follow. Obviously, in this case of the mechanical splicing, fibers are crimped to hold them in place and do not have strong fiber retention or pull-out strength. And that may be the reason why, that may be identified as the reason why mechanical splices generally have higher loss and greater reflectance than the fusion splices. The splice component itself includes a precision alignment mechanism, as we said. It's more expensive than a simple protection sleeve that's needed for the fusion splice. So what we're talking about here, as you will see in the case of fusion splice, you're going to use some sort of a protection sleeve that's going to provide a mechanical strength to the fusion splice, and that sleeve is generally much smaller than the actual a fixture that's being used for mechanical splice, and that's been shown here on this slide. So there's obviously certain advantages of fusion splicing relative to the mechanical splicing. So the question is, why is mechanical splicing used at all? Well, there are certain advantages or certain applications where mechanical splicing will be preferable relative to the fusion splicing. One obvious advantage of mechanical splicing is that it's more affordable, cheaper, as opposed to the fusion splicing, where in order to perform the fusion splicing, you have to have a fusion splicer, which is a device that is relatively costly. It may cost thousands of dollars. So if you are a fiber optic technician that's going to be doing many optical splices, and that's going to be your primary responsibility, then buying a fusion splicer and doing investment into a fusion splicer may be a good thing to do. However, if you are going to be doing splicing just occasionally, that's not your primary responsibility, then investment into fusion splicer may not be justified. So in such a case, you'll most probably resort to the mechanical splicing. Another reason for using mechanical splicing is if you need to establish some sort of fast or temporary restoration, or if you are splicing multi-mode fibers in a premises installation. So mechanical splicing, in a sense, can also be considered as some sort of temporary joint that has to be established in certain applications. Also, if mechanical splices are not crimped, they can also be used as temporary splices for testing bare fibers with OTDRs or OLTSs, etc. So the advantage of mechanical splices is they do not need an expensive machine, expensive splicer to make the splices, as already elaborated. A relatively simple cleaver and some cable preparation tools are basically everything that you need to provide to perform the mechanical splicing. Very often you would also want to have some sort of inspection tool, such as visual fault locator, to kind of double check the success of your mechanical splice and eventually optimize some sort of splices if optimization is needed. Here are a few different types or mechanisms of mechanical splicing alignments. There's many different vendors out there that are offering tools and equipment for mechanical splicing. Here some that are some are mentioned on these slides. So one of them is so-called capillary tube. That's the simplest method of making a mechanical splice, where basically two fibers are aligned in a small glass tube with a hole that's slightly larger than the outside diameter of the fibers, and it's going to be used to put the index matching gel that's going to establish the connection between the two splices. There's also a YouTube video link here that I would strongly advise you to watch to kind of get a better feeling of what we are talking about here. Another technique is so-called fixed V groove, where we are basically working with single fibers or even fiber ribbons. So you can do a splicing of a group of fibers at the same time. This is also a very simple and technique that works pretty well. The groove alignment plates can be made of many types of different materials and are quite inexpensive. So a very affordable type of technique to be used to align fibers before mechanical splicing is performed. Here are other two mechanical splicing techniques. The 3M fiber lock is a version of the V-groove splice that uses metal stamping inside a plastic case to align fibers and to crimp them. This is considered an elegant design, and good performance has made it one of the most popular mechanical splices. And finally, Corning, as one of the main manufacturers of fiber optic equipment and cables, also have their own so-called GTE elastometric splice that's going to use soft elastomers to hold the fibers in a position. And this technique is kind of similar to the fixed V groove, It's just that the grooves in this case are soft, so they can easily accommodate slight variations in the fiber diameter. And two more techniques. AT&T has been offering so-called rotary splice that looks more like a connector. In this case, fibers are glued into a glass ferrules and then polished and finally inserted into some sort of alignment sleeve. And finally, they would be rotated until the lowest loss is obtained. So this so-called tuning the splice. Obviously, there are certain aspects here that have to be taken into account, such as the complexity and the cost, and also labor, so that these types of rotary splices are not so popular as some of other techniques that have been previously described. And the last mechanism that we're going to mention is light creamed offer by Tyco. These splices are used in the commercial industry for new installations and repair of telephone company central offices, interbuilding backbones, and the customer premise applications. We are now turning our attention to another type of splicing, and that's so-called fusion splicing. In order to perform a fusion splicing, you need a specialized type of instrument, so-called splicer, that's going to be used to fuse the fibers together. Fusion splicers basically use an electric arc to weld two optical fibers together. The process of fusion splicing involves using localized heat to melt or fuse the two ends of the fibers together. So this slide here shows a few pictures of fusion splicers, and also on the bottom left corner you also see the actual process of fusion splicing when a high electric arc has been created that would basically melt the glass and establish the permanent connection between the two optical fibers. So how is fusion splicing performed? So here we are talking about an electric arc that's been created by a high current that is going to ionize the space between the prepared fibers, and that process is going to eliminate the air between the two fibers, and it's going to heat the fibers to the proper temperature of about 2000 degrees Celsius. So you can see the whole process of splicing shown here on this slide, where you see a high arc, this high light that's being created between the two electrodes that would, as already explained, ionize the air and then heat the glass and ultimately melt the glass and establish a fusion splice. The two electrodes that I used to perform the fusion splicing are replaceable parts. They have to be replaced for about 2000 arcs for a typical splicer. And that's something that should be managed as a regular maintenance of your fusion splicer. Finally, after the fusion splicing is performed, you are going to use the plastic sleeve with the strength member as a protective device that you're going to put over the fusion splice that's been performed in the previous step. This process of placing plastic sleeve over the fusion splice generally requires controlled environment, including the actual fusion splicing. So usually fusion splicing is performed in some sort of splicing van or trailer if you're doing fusion splicing out in the field. Use of that type of controlled environment would reduce the possibility of dust or any other contamination that may be present in certain environments in which fusion splicing is going to be performed. So here's a little bit more information about fusion splicing. So again, the whole procedure described. So we first have to prepare each fiber end for fusion. Fusion splicing requires that all protective coating be removed from the ends of each fiber. So we're going to perform the process of fiber optic stripping of the optical fiber, and then cleaving or cutting with the precision cleaver to make a very clean end face of the two fibers that are to be fusion spliced. Once the fibers are cleaved, you'll place them into special holders that may be either removable holders that you can take out of the fusion splicer, or are part of the fusion splicer. So if they are removable, usually you would install the optical fibers into the holders and then load the holders into the splicer. The splice is usually inspected via magnified viewing screen. So once the splicing is performed, the splice joint is going to be checked, and also loss through the previously established splice is going to be measured. It's also important to mention that splicers usually have small motors that are going to be used to align the end faces of the two fibers together before the actual fusion splicing is performed. So this slide goes a little more in detail about the whole process of alignment during the fusion splicing. Fusion splices are usually used with multi-mode fibers, but also single-mode fibers can also be spliced. And usually in the case of a single-mode fiber, since we are dealing with a smaller glass core, there's an additional level of difficulty that exists in the whole process, because the alignment has to be performed in a very accurate way. So in the case of multi-mode fibers, it's sufficient to align the claddings to achieve a low splice loss. However, in the case of single-mode fibers, there is demand for the cores to be aligned. So the whole mechanism of alignment mechanism in a fusion splicer has to be performed in a more accurate way. The best fusion is to achieve the best fusion requires a lot of precision. So it's a complex matter that involves not only precise alignment of the fibers, but also careful application of the correct arc, discharge, power, and timing. That's why it's important for your electrodes to be properly maintained. An incorrect discharge, for example, would deform the cores and create unacceptable loss through the connection. Splicer also have adjustable power and time to accommodate different fibers and application needs. So you have to be familiar with the fusion splicers that you're going to be operating on, not only to perform the blind fusion splicing without really understanding how the whole fusion splicing is performed and what are the capabilities of your fusion splicer. As I said, adjusting the power and the time would result in much higher quality of your fusion splices that you're going to be performing out in the field. So once the faces are aligned through some sort of alignment mechanism, the splicer is going to emit a small spark between the electrodes at the gap to burn off dust and moisture. So that's the first step during the whole splicing process. Then splicer generates a larger spark that would raise the temperature above the melting point of the glass. We're talking of about 2000 degrees C, and finally the ends of the two fibers will be fused permanently. The location and energy of the spark is very carefully controlled so that the molten core and cladding do not mix, and that's going to minimize the optical loss. This is especially important in the case of single mode fibers. And finally, the splice loss is estimated by the splicer. You will see it on the screen. Common techniques for loss estimation are, for example, directing the light through the cladding on one side and measuring the light leaking from the cladding on the other side, or by taking measurements of the physical properties of the completed splice from the fiber image and using certain algorithms to determine the splice loss. So all this is going to be performed after the splice is being done, and usually you'll see the results on a small visual screen that's part of your fusion splicer. Last portion of this lecture is going to cover yet another aspect of a fiber optic link connections, and those would be fiber optic couplers. So after we have described the process of optical fiber splicing, we are switching gears to fiber optic couplers. So why are we using fiber optic couplers? Certain fiber optic data links would require more than simple point-to-point connection, where you have one optical fiber that starts with one single port at the transmitting side and then one single port at the receiving side. these types of data links that require multiple connection are usually characterized by a more complex design, and in those cases you are using special types of connections that would enable combining or splitting optical signals into multiple optical fibers throughout the system. So that's where you're going to find the use of devices that are commonly known as fiber optic couplers. So how do we define the fiber optic couplers? We are talking about device that can distribute the optical signal or power from one fiber among two or more fibers. Fiber optic coupler can also combine the optical signal from two or more fibers into a single fiber. So we can have either a combiner or a splitter that are going to be two specific applications of a coupler. Fiber optic couplers attenuate the signal much more than a connector or splice, because the input signal is divided among the output ports. So that's also important to recognize. Every time you're splitting optical signal, obviously that the power is going to be split in different ways. So in a sense, if you have one input and multiple outputs, obviously that the power levels at the two or multiple outputs will be significantly lower than a single input. So that's just one example of the fact that optical couplers attenuate the signal during the whole process of splitting through this type of a device. It's important to mention that fiber optic couplers can be either active or passive devices. What is the definition of an active or passive device? There's a common definition that is applicable to the entire field of telecommunications. So we are talking about a passive device as a device that redistributes the optical signal without any kind of optical to electrical conversion or amplification. On the other side, active couplers are electronic devices that would split or combine the signal electrically, and then they would use fiber optic detectors or power sources that would turn electrical signal into optical signal, or they may be also the other way, where the optical signal is transformed into electrical signal and then split or combined. So in general, fiber optic coupler may have, in this case, a certain number of input ports and certain number of output ports, where the number of input or output ports range between 1 and 64. The number of input ports or output ports can vary depending on the specific application of the coupler. There are many different types of fiber optic couplers, such as optical splitters, optical combiners, X couplers, star couplers, tree couplers, etc. So different configurations of these types of combining or splitting devices that have found different applications in the field of fiber optic communications. If we are talking about an optical splitter specifically, we are talking about a passive device that is going to split the optical power carried by a single input into two or more output fibers. Usually we have one input and two outputs. In such a case, we are talking about so-called Y coupler, or if we are distributing the power in an uneven manner, we can also be talking about the T couplers or so-called optical taps. So there are different configurations of fiber optic splitters that are out there that you should be familiar with if you are going to be dealing with this specific aspect of fiber optic communications. On the other side, if you're talking about fiber optic combiners, here we are combining the power from multiple optical fibers into a single output fiber. So in this case here on the slide, an optical combiner is shown where we see I think 8 inputs, 8 optical fibers that are then being combined into one optical fiber at the output. This slide goes a little more into detail about different configurations or types of optical couplers. So we have X couplers that would combine the functions of an optical splitter, and combiner would have multiple inputs and multiple outputs. Usually we have 2 inputs and 2 outputs in the case of a X coupler. We may also have a star and tree couplers that would be multi-port couplers that would have more than 2 input or 2 output ports. So for example, a star coupler would be a device that distributes optical power for more than 2 input ports into several outputs, while the 3 coupler would be a device that splits the optical power from 1 input into more than 2 output fibers, or vice versa. So different configurations. You probably can already recognize why a certain coupler is called the way it's been called. Obviously it has something to do with the configuration or with the way how it looks, that is directly related to the number of inputs and outputs that are used on a specific device. And finally, a few comments about optical fiber fabrication. Without going too much in detail, it's important to remember and recognize that we are talking about fabrication techniques that can be very complex and difficult to understand, may involve a whole bunch of different techniques such as twisting, fusing, tapering optical fibers to provide a certain action of combining or splitting of the light when it's being propagated through these types of devices. And finally, at the end, let's quickly summarize this lecture. So today we talked about two categories of fiber optic connections. We talked about fiber optic splices and fiber optic couplers. The first portion of the lecture covered fiber optic splicing in detail. We explained the whole process of fiber optic splicing. We elaborated on two specific types of splicing, so-called mechanical splicing and fusion splicing. A few slides covered mechanical splicing in detail, how it's being performed, and different techniques to perform mechanical splicing. And then we switched gears to fusion splicing. We explained the fusion splicer as a device that's being used to perform the action of fusion splicing. We covered in detail different steps that you should go through during the fusion splicing, such as the alignment, applying the high arc to melt the glass, and finally check for a loss in a previously established fusion splice. And finally, at the end of this lecture, we also covered the aspect of fiber optic couplers. That is a third category of fiber optic connections that are used in fiber optic communications. We described different types of optical couplers and their applications. We've seen that fiber optic couplers can have multiple inputs and multiple outputs, and in that regard, they have different. They are labeled in a different way, from X couplers to Y couplers to star couplers, 3 couplers, etc. And finally, we also made a few comments about the fabrication of optical couplers. So this concludes lecture number 6. Next time, in lecture number 7, we are going to be talking about optical measurements. So once the proper installation of a fiber optic link has been performed, you will do a certain measurements to check or inspect fiber optic connections and see whether you are within a certain loss budget that has been established by the project that you are part of. With this, I'm going to conclude lecture number 6. I will see you all next time. Have a nice rest of the day.